I'm going to kick it off with Mitch Fourman. Thank you, Mitch, for being here with us. And Mitch is going to give us a little intro to AI.
Dr. Coleman, thank you so much for having me, and it's a privilege to be a part of this panel. Um, my goal with the 8 minutes that I have is to try to go over some of just the terminology regarding AI, which is this very exciting thing that we're seeing that's affecting all of these different fields around us. No, healthcare is certainly not spared by it. There's some terminology I think that is very useful for us, especially as we delve into some of the research that's coming out, large scale databases, what have you. And so we'll try to touch on these. I have no conflicts of interest related to this. Uh, Artificial intelligence, by definition, is to accomplish tasks that typically would require the decision-making input of a human. Those tasks, if you think of them, what clothes to wear in a day, what the likelihood of rain is, should I bring an umbrella, or something as simple as does my car need oil, involve basic steps, which involve learning, experiential based learning, reasoning, perception, experiencing the world around them, and then natural language processing, expressing that. And so really any decision that we make, any communication that we have involves these four steps, and that's no difference for what AI's goal is. And the levels of AI that we're at right now are a very low end of it. It's able to perform tasks within a very narrow range of functions that we define. It's not able to generate tasks for itself. It's not able to create things that we didn't create it to do. It's essentially able to work within a narrow band of tasks that we identified. Within the future end, the next 5 to 10 years, perhaps we'd be looking at more stronger AI things that are more human-like, that can cross over, can perform a broader range of tasks. And then, of course, the theoretical ones we see in the movies, the super intelligent, the ones better than us in every way. And perhaps one day I will salute our new robot overlords. AI currently used falls into a lot of different categories, but on the right side, really the big three circles matter the most, which is artificial intelligence, the blanket term, machine learning, what you probably see mostly highlighted in research and some of the clinical algorithms we have now, and then deep within machine learning, a more complex category called deep learning. Netflix is the easiest one, and one that I found cited repeatedly is a great example of a machine learning algorithm, which is that it's provided with a certain type of data, which is the movies that you like, the preferences that you have, and then it creates an algorithm that tries to project what type of things is the most likely thing you're going to watch next. And so that's why everything that I click on is the thing that I wanted to have watched. A nice quote that I see quoted in a lot of textbooks I thought that was worth copying verbatim was, a computer program is set to learn from an experience E with respect to some task T and a performance measure P, so that if the performance in the task is meant to improve, it improves with experience. And that's by definition what machine learning is supposed to do. And within machine learning, you have supervised learning, unsupervised learning, and reinforcement learning. Examples of things that go a little bit deeper down into the brush include large language models like ChatGPT, where now it's looking at larger data sets to process human language, which has a lot more intrinsic variability, trying to parse individual words and sequences down into patterns in order to identify what it is the most likely responses to be. Current large language models that we have tend to try to predict what it is that you're trying to think of and move forward, which is why they tend to be quite supportive and why we run into problems with the thing agreeing with us with everything you say. Google Translate is a deep learning algorithm, another type of machine learning and artificial intelligence, an artificial neural network, which is meant to process data. And there are a lot of different types of deep learning algorithms. There isn't just one. There are 10 larger ones used. To kind of highlight two of them here, one of the more common terms you'll hear is the convolutional neural network, which is the idea where you filter process an image by sliding it across the image to produce a map. You continually slide over and over again to process these maps in order to contain the most essential of that information, and then you output that. And so all deep learning algorithms have the input, the picture you're looking at, or the data you're looking at, the hidden layer, which is the processing of that data, and the output. Another example is the recurrent neural network. That goes a little bit deeper than what I think we need to really go into. Really, the basic things that are worth looking at, the things that you'll see in papers, the things you'll experience with hospital studies, fall into two major categories, which are going to be supervised learning and unsupervised learning. Supervised learning you do already, and we do it all the time, and we don't even think about it, but it's a form of machine learning, which is that you have data that is labeled, your input data, and your output data that is labeled. You're not asking the algorithm to figure anything out. You're asking the algorithm to provide values within a certain group of data that you have very highly curated and then create an output that you have already designated. And so we do this a lot in analyses and don't even think about it as machine learning, but these are regressions with linear regressions and classifications, which are logistic regressions. Those are things that we do again, not thinking of it, but they are a type of machine learning, a very highly supervised version of it. Unsupervised learning is there's no teacher, there's no label. The idea is that you're giving the system a very significant amount of data with lots of variables attached to it, and you're telling the system, figure it out. Group them together. Tell me something unique. Find the variable, the factor that is something that could be something that we didn't even really think of. And so the most common one that you see a lot and the sexier thing that's being used a lot is the cluster analysis. I put in a ton of patients that have all different types of spinal deformity, all different types of lumbar stenosis, all different types of socioeconomic characteristics. And I tell the system, put them together, find me my phenotypes, find me the things that are worth analyzing. It's not looking for an outcome, it's looking for uniqueness and patterns within data that it doesn't actually have a definition for. And so there are therefore very distinct reasons why you might use one versus another. In a supervised model, you have a testing cohort, you have a training cohort, you have a better idea about whether your accuracy is reasonable because you can train your model and then test it on a group of data that you didn't train off of. It creates a desired output because you've told it what it is that you're looking for. You've assigned it labels. It's a more simple analysis. We know how to do regressions. We click it in the system. We have a lot of different easy statistical platforms that you just highlight the data you want and it punches it out for you. I mean, everything down to GraphPad Prism, which is a very simple one. It doesn't take a whole lot of experience to do those things. And then more importantly, you have an analysis that's easy to understand. The input and the outcomes are clear, and you're trying to find an accurate way to highlight that outcome. By not labeling, you're opening up your algorithm to find things you haven't considered, which is pretty cool. But it's important to note that you're not looking for an outcome, but you're looking to find associations within that data. You might then look to see whether the outcomes matter, but that's not what the model's for. Important to note within AI is that if you have put garbage in, you're going to get garbage out. And it's important to have interpretation of that data and generalizability. If you put data that's too niche, you're only going to get an algorithm that's too niche. It's not going to be important to what you're looking at. So to try to curate things a little bit better, you go into a term feature engineering. You do this already. We know it. You're looking for data that's missing. How do you find the errors, the inconsistency? You look for the data fields that aren't in the right spot. You're going to transform data. Maybe I don't want to know what every single age is doing. I just want to know what a classification of a specific age is. You're going to find features that are given in these very large multifactorial variables, but you only really want one of them. And so you clean that up a little bit more. And so we do this in any real good study before we even start doing the actual analysis. And so feature engineering is part of model generation, but it's also part of iteration. The better you make the data, the better the model. Components of feature engineering are things that we do. You just didn't know the term for it, which is one-hot encoding, which is the idea that you're taking a large number of categorical variables and then turning it binary. So maybe I don't need to measure red, green, blue, white. Maybe I just want to know who's blue. And then you get the 1 versus 0. You bin patients. Maybe I don't care how many patients within this large sliding scale of technical infinite BMIs. I really just want to know who's morbidly obese above 35 or who's normal, overweight, or obese. That tells me a lot more information than the number of things I need to see. And then finally, feature splitting is I'm not going to take the whole address. I don't care what street you live on. I care about your zip code because then I'll be able to look at your census district and figure out your area deprivation index or whatever census related variable you're looking for to measure overall regional socioeconomic deprivation. Once you've created the model, then we have to actually figure out what you got. There are different types of way of doing that. The way we see a lot within manuscripts, I think in spine in particular, is the train and testing. The idea that, the 80-20 split, the training to the 20% testing cohort. There are different reasons why you'd want to change that percentage. Not everyone goes by that, but the 80-20 seems to be the more common one. There are ways for smaller data sets you can do cross-validation if you really want to go deeper into the weeds a bit. Try to split the data and then effectively permutate it to run the same model off of different groups of patients. And that way you actually get a little bit of an idea about how well the model works, and you can use a smaller sample size to achieve the same degree of analysis. Beyond the idea of validation is the idea of calibration. If I'm going to predict a model that says I'm going to find something that occurs roughly 60%, I want to know that it occurs roughly 60%. You should have a general idea of your outcome when you're starting to generate these things. But calibration of the model isn't just looking at the accuracy, it's looking at the ability for it to be confident within that and to stay within an hour variation. It almost follows the Six Sigma rule. You're not about trying to be accurate, you're trying to minimize variation. Models can be overconfident, which is it just shoots the moon, like in this left column here, where it gives you a perfect likelihood of one and no likelihood of another. That's not really what you want. Could be underconfident, where it's lower likelihood across the board, but really the accuracy should be 70%. All of these are well below it. And then the both, which is the over and lower. It should be 70%. Here it's 100. It should be 70. It should be 40. It shows a little bit of an over and an under calibration. And that means you got to come back and you got to try to iterate things a little bit. You need to, in that way, understand what it is you're iterating and what it is that's wrong with what things are there. So there are a lot of different ways of measuring calibration. You have the Breyer score, which is this mean squared difference between predicted outcomes. Log loss, looking at how degree of confident things that were wrong were. So if you had the system say with 100% certainty the answer was yes, but in fact the answer was no, it gets penalized for that. And then the calibration curve, which we're a lot more familiar with in general, which is looking at the difference between the predicted and the actual probabilities. The calibration error, this deviation from the expected, is as small as possible. Then you have something that's a pretty well calibrated, tightly looking model. The one thing that we see in a lot of analyses, as well as the area under the curve, the thing we tend to most best understand, which measures the way one, or in this case, several models, try to distinguish between a binary outcome over a range of probabilities. You want an area under the curve of one, this gold line that makes that nice, neat curve is an example of one that gets pretty close. But in many cases, you don't have that. And so this variable here is an area under the curve of 0.7. What this says is that if you have a group of analyses techniques using the same like modeling techniques using the same data, that model just didn't work very well. If you get a variable close to 0.5, you're at that point at random guessing. And so the model is not particularly useful. All in all, none of these words should be entirely great takeaways. My goal in understanding this is not to be able to do every aspect of machine learning. There I have great statisticians I work with. It's to be able to read what they're outputting and trying to understand what it is that's on the page. Because ultimately it's my name that's on the publication. It doesn't matter if I generated this or not. You have to know the topic. If you're generating data, and it's a difference between a data scientist that's purely within the vein of data science and a clinical scientist, if you don't understand what it is that you're analyzing, you're going to produce data that's effectively junk because you just don't have an idea of what your outcome should be, and you have therefore no way to assess your validity. If you don't clean the data, you're not going to get a good product. If you just dump everything you have in an Excel sheet that got collected and you didn't do a whole lot to curate what you have, you're going to get garbage in and you're going to get garbage back. You got to make the model as useful. If I create a predictive algorithm for creating durotomy, I'm not sure how great that is if I didn't include the complexity of the surgery and and understand surgeon-specific factors. Because ultimately, you can have little old lady more likely to get dural term, maybe, but ultimately, if they had a 9-level surgery versus a 3-level surgery, maybe that's a bigger variable in that as well. The last thing is I think it's worth mentioning that bias does exist. Drift is the most common one, which is that you spend all this time creating a model to predict your surgical outcomes, and then the surgical technique changes. And so therefore the whole model drifts and you've basically created something that was antiquated. And that's a whole big problem in a field where, like in spine, 25 years ago, we had our FDA approvals for pedicle screws. It's something that is all brand new to us. And so we are changing constantly, and therefore it's important to concede the fact that sometimes the things we analyzed last year are simply just not the facts on the ground. And then finally, the bias really comes into play is, did you create a simple model that analyzed something that was more complex and needed more data? If you included only 3 variables looking at admission rates, you probably didn't create a good enough model, even if the area under the curve looks beautiful and the rest. I think we have to be realistic about the things that we're including. And so long as we understand that machine learning is a beautiful thing that can help us identify things that the naked eye can't necessarily show, and is a much more complex and I think in many cases robust analysis technique that we have access to, and we still have to understand that it's what we put into it that actually matters. This was a quote that I learned while I was Dr. Schwab's fellow over at Mass General years ago. His postdoc once told me, and I love the quote more than anything, that he loved machine learning because no matter what, he's always right. And the simple fact is, if you look deeply enough into things, you will find significance. The point of humans and why we're at a low level of AI versus what we could be seeing in the future is that we have to look at the things that are given to us and understand what is there. And ultimately, sometimes it's just not there. And sometimes it found something we never even thought. Thank you all. Hopefully I stayed somewhat reasonably in time.